to start up. If you're joining me live, I want to appreciate it. My name is Frank Lavinia, and I'm looking for my fancy captions here. Here we go. My name is Frank Lavinia, and if you're just joining me live, I appreciate that. Just giving it a second for folks to join. And today, if you can tell from the title, we are going to be talking about qubits. So let me take a look. And start sharing my screen so we get started. Awesome. I need to change this graphic to include impactquantum.com. Yes, boys and girls, we have a domain name now for the podcast. So if you're not familiar, Andy Leonard and I do two shows now, two podcasts. One is Data Driven, which is 3 years old, 150,000 downloads or so, and 256 episodes. Impact Quantum is a new show that we started, and it is brand new. This will be show number 2. There was show 0, so I guess this would be the third show. So let me kick off the cool graphics so I can do the editing later. It saves me time. All right, I might have to run the dubstep thing again. Hang on. As you can tell, I do enjoy my fancy graphics. So I'm going to run it one more time for apologies. All right, let's get this started. All right, so that dubstep intro music means that this is Impact Quantum, the podcast for engineers who are curious about the coming revolution in quantum computing. I'm your host, Frank Lavinia, and my co-host will not be able to join us today. So as we promised in kind of the original show, we're not going to kind of do that. We're going to try to get to a more regular cadence in these shows. So this is show number 2, although technically 3rd in the series. This show was rated 2 Schrodingers because we will get into a little bit of technical detail, but don't let that scare you off. I'm going to talk about qubits and how they work. My name is Frank Lavinia. I'm a data and AI architect who got quantum fever not that long ago in November 2019. When I saw kind of the amazing stuff that's just around the corner. So today is about qubits, and there's a whole meme about this. The original song referred to magnets, but I think if they were writing this song today, they would be writing this about, they would write about qubits. Hang on. Spotlight a performance. Hang on. Hey, cool. It does that now. All right. They took my feedback. Let me start this over. If you're watching this live, I really appreciate it. I will be monitoring the chat. Hey, Modern Day Tech. How's it going? If you're watching this live, I appreciate you turning in live. If you're listening later on the podcast, I will try to be very descriptive in the time that I have between now and my next meeting. All right. So, if Insane Clown Posse were writing a new song today, they would probably talk about freaking qubits or how do they work. So there's a whole internet meme about it. To paraphrase something from one of the Guardians of the Galaxy movies, they didn't say frickin'. You have been warned. So this is a part of my big quantum presentation called Quantum Physics in 30 Minutes or Less. For people who have mixed feelings about advanced mathematics. This is the big barrier, I think, for a lot of folks when they want to get into quantum computing. There's a lot of math. There's a lot of weird kind of quantum physics. And you hear a lot of things said about quantum if you do a search on the internet on quantum, there's all sorts of interesting kind of metaphysical stuff. Not going to touch into that. But what makes quantum weird is how we normally interact with the world. We normally interact, whether it's a baseball, whether it's the moon. We interact what's known as Newtonian or classical mechanics, right? If I held this smartphone, right, and I drop it, it's going to fall to the floor. Maybe the glass will break, maybe it won't. But it's not going to, if I let it go, it's not going to go up and blast off and hit the ceiling. It's not going to stay there in place. If I were to able to throw this fast enough, I would be able to get this to the moon. If I could throw this a little bit less faster than that, I could get this into orbit, right? So that's kind of how things work, right? If I smack it against my other hand, it's going to make a noise and possibly hurt. But we can all measure based on the mass of this and the acceleration, how hard of that force is going to hit across the hand. I guess if you're really clever, you can even figure out how loud that smack would be. So quantum mechanics deals with stuff that's really, really small. Basically, smaller than an atom or at the atomic level, right? So at this point, in our normal world, here's kind of the scale of a human hair would be 100 micrometers. Then we get down into kind of the genes and the viruses, somewhere between 10 to 100 nanometers, nano being a billionth. And viruses are obviously very much on people's minds these days. But smaller than that, smaller than proteins, you get molecules, small molecules, and atomic structures. So inside that atomic structure is where things kind of start getting different. And I actually did listen to while I was on vacation, I read a book on quantum computing, an applied approach. Interesting book. But there was an even more fascinating book called Synchronicity. And it's about kind of the understanding, the reach to understanding how the universe works, from Plato, kind of talking about, the forms in the cave and all that kind of philosophy 101 stuff, which, obviously, at that time was very cutting edge, all the way to kind of where we are now and how we understand stars and fusion and quantum physics and particles and stuff like that. So those are all the things that we have at multiple levels of understanding. So over time, we've really gotten down to, we've always pursued the forward march of science, if you will. So quantum physics works a little differently. And that book, Synchronicity, really covers the weirdness of quantum mechanics and the struggles that 20th century physicists went through to understand it. In fact, this is something that Einstein himself was very skeptical of. You'll see that probability plays a big role here, and Einstein was famously quoted as saying that God doesn't play dice. And so there's definitely a lot of interesting kind of interpersonality conflicts too. One of the gates is called Hadamard Gate, and they talk about him. There's also 3 types of poly gates: poly X, poly Y, and poly Z. And I wondered who is this guy, Poly, that has so many quantum computing logic gates named after him. And this book actually covers who he was. Kind of a big deal. Not a household word, but still kind of a big deal. So what quantum computers do is they take advantage of some of the quirks, if you will, of quantum mechanics and the properties thereof. I did warn you that this episode was going to be to Schrodingers. We will talk about this stuff. I don't fully understand it, but I do understand a good bit of it, and we can kind of go through some of the particular properties that this matters. So ultimately, quantum computers take advantage of all of the strangeness, if you will, for lack of a better term, of quantum mechanics. And in the same way that classical computers, whether it's your smartphone, the laptop I'm recording this on, take advantage of the properties of electricity, right? They are called electronics after all, and there's little electrons bouncing around inside those things, and we take advantage of how that works and how semiconductors work. So there's four or three kind of properties that really matter, and then all of these operators are kind of built on that. And then when I say operators, I mean logic gate operators, like you would have with and not type of gates. Stuff you really would only learn in either electrical engineering or kind of comp sci kind of intro, to just kind of show you how things ultimately happen on the actual metal of the chip. All right, so the first element of this is really called a qubit. And what you're seeing here is a bunch of math focused on kind of basically discussing the state of the wave. When you see that character, that means the state of the wave. This is basically the probability of it being, or the state of it being 0 and 1. And ultimately, how does that work? Right? So in a classical bit, and this is everything, every computer you've ever used uses classical bits. Basically a circuit is complete or it's not, right? The gate is on or the gate is off. Now, what makes qubits special is they have the ability to also be 1 and 0, right? Based on the electron spin. But there's another state, a third state, if you will, where it can be both 0 and 1 at the same time. This is called superposition. And there's a famous thought experiment called Schrodingers Cat. And basically it kind of breaks down into, until you examine, there's a cat in a box, the cat may or may not be dead, but until you open the box and observe it, the cat exists in both states. The cat is both alive and dead simultaneously. This is kind of a combo state. And this is 0 and 1, right? Cat is dead or the cat is alive. And there's kind of this combo state of uncertainty, basically, where it can effectively be both 0 and 1. And there's a great scene from the movie No Country for Old Men. And basically it is, this guy is a very threatening kind of bad guy. And he flips a coin. Why is my animated GIF not playing? That's disappointing. But I guess if you're listening along, this character here basically threatens this guy and he forces him to call the coin. And then ultimately what happens is he calls it and he gets it right. But the cinematography, the lighting, the tone, the music all really paint the thing that this guy could die any second. And it turns out that he made the right call on the thing and the guy just walks away. It was a very bizarre moment in the film, in a very kind of strange movie. But at that point, when we didn't know, we weren't certain of the outcome of the state. So that's kind of another example of kind of that uncertainty of state there. All right, so I did warn you that there is some math ahead. And this is the first time we're going to do something kind of highly technical, both as a live feed on LinkedIn, YouTube, and Twitch, of course, LinkedIn. But we do have, I will explain it in my humble way. If you think I'm doing this wrong, I very may well be doing it wrong. But I would encourage you to come on the show and explain it the right way. I am not a quantum physicist. I am not a particle physicist. And I know math of AI, and that's where I land. All right. So superposition is the idea of how does that happen? Well, mathematically, ultimately, superposition is the state of both 0 and 1. So in other words, superposition is 0 plus 1. Now, I learned in kindergarten that 0 plus 1 is 1, right? Or 0 plus any number is the same number, right? So how does that work? That doesn't make any sense. And this, for me, this is the aha moment I had, because I attended a talk where he explained it very well. So you're right. If you're adding integers, absolutely 0 plus 1 is just 1, right? There is no third state. However, what if you're adding vectors? Now, if you are watching this, or you're listening to this rather than watching it, think of a 0 as a horizontal line, right? And if you were to describe that in Cartesian coordinates, that would be 1, 0, right? So that flat line is noted in Cartesian coordinates as 1, 0. Now, a vertical line, that is going up and down, would be described in Cartesian coordinates as 0, 1. So 0, 1 for a vertical line, and a 1, 0 for a flat line. Just think back to middle school math when you were drawing plots and charts and stuff like that, and you all thought it was useless, right? All right. Adding those two states together, you get superposition, right? So think now of a 45-degree line that goes from can be described as 1, 1. Here's the rub. You're not adding integers. You're adding vectors. And once you start adding vectors, you get to some interesting points of math. And this is basically called linear algebra. Some people call it matrix math, but essentially it's the same thing. And what you're defining here, this is called bracket notation, which, if you're wondering why Amazon called their new quantum service bracket, this is why. This is known as bracket notation, where you have the pipe, a letter denoting a variable, and then it's not quite a greater than sign, but it kind of looks like one. All right, hopefully that makes sense. So vector math, or matrix algebra, has some very different, has some very well-defined rules. They're a little bit different than the math you learned, in kindergarten and elementary school. Matrices, or not matrices. Well, yeah, it is a matrix. So these vectors, these vectors can be represented as matrices, which have their own rules in terms of how they're multiplied, right? So what you're seeing on screen is that if I have a line that's defined by 1, -2, and I double that, I now have 2 and -4. Yeah, this is really difficult to explain in a way that folks on the podcast will get value out of. But ultimately, it boils down to, turns out that you can get quantum problems can also be represented in this matrix math or linear algebra, right? So if you express the problem in that, and what you're seeing on the screen, if you're watching on the screen, is the math behind adding up these vectors. So ultimately, at the end of the day, quantum computing, indeed quantum physics in general, boils down to matrix math or linear algebra. So if you already have experience with this, you are in good shape for the future. If not, it's a good time to learn. All right. So this is the second part of qubits, and this kind of gets into kind of the nomenclature and common descriptions of it. Basically, mathematicians just love Greek letters. I don't know why. The short of it is that the Greek letter psi is used to represent the state of a qubit. Greek letters alpha and beta are used to represent the numbers, or at least their placeholders for that, for the matrix. For the matrix, yeah, for the vectors. Every time I get stressed out and confused about this, I kind of take a deep breath and think, this even bothered Einstein. So I feel good. I'm in good company. All right. So this is what superposition would be defined mathematically. So the idea here is that um, you have the state of a qubit is equal to the likelihood of it being in state 0 or state 1, the addition of the two. That is basically kind of what it is. And then in this example, this one does make sense to me, even though there's all sorts of weird square roots or whatever. But ultimately, there's a 50-50 chance of the state here, psi, being 0 and 1, right? I guess that's pure superposition. And I should probably find a more eloquent way to describe this verbally for those on the podcast. But short of it is that all of this can be worked out mathematically. And what's interesting about this is that long before computers that we have today were worked out to how to use binary, how do you build a logic gate or whatever, it was worked out mathematically. I want to say like a century before transistors actually came about. So the fact that we can kind of see how the math works out and kind of work through these, how a quantum computer would be architected to solve these problems, is very much a callback to where we were a century ago with computers. All right. So speaking of that, I'm going to talk about operators. So if you go back to kind of the original world of not that screen. I mean old school stuff like this, right? So if you had to read or write schematics, this is basically the classical logic gates. And so this is a NOT gate, right? So it would be inverted, right? So if I sent in, a 1 out, a 0 would come out. And then these are the other gates. This ultimately is what powers, this type of logic is ultimately what powers everything that you've ever seen done electronically. Whether that's, you're streaming the new season of The Boys on Amazon Prime, arguing with people on Facebook and Twitter, or listening to this podcast right here. Everything boils down to a lot of these fundamental gates. And this is not all of them, but ultimately, this is a big chunk of them. All right, so what does this mean? So because you have that added superposition state, there's all sorts of new possibilities that are opened up. And these new possibilities can, in turn, create new algorithms that have not yet been invented. So here I mentioned before poly X, poly Y, poly Z, and the Hadamard Gate. I'm not quite sure exactly what poly X, Y, and Z do. I am still studying, but I do know that a Hadamard Gate will take a qubit that's in state 1 or state 0 and basically launch it into superposition. Now, here's the weird thing, and I'm not ready to talk about this in any length. If you chain Hadamard gates together, right? So if I take a qubit, run it through a Hadamard gate, that qubit is now in superposition. What happens if I put it through a Hadamard gate again? If it's already in superposition, does it have no effect? Does it not have an effect? It turns out it does have an effect. I don't fully understand it, so I'm not going to explain it. I have to rewatch the video again. But ultimately, that's kind of it. So just know two things. If you take away nothing from other than my awkward explanation of vector math or linear algebra, take away that because we're dealing with a new kind of fundamental element here. I don't like the word element, but classical computers used electrons and their properties. Quantum computers will use quantum mechanics, or the quantum level particles, or at least particles that are not ruled by our world of classical mechanics, right? Again, think of the phone, right? If I throw the phone against the wall, it'll hit the wall. If I throw the phone hard enough, it'll break through the wall. If I throw it fast and hard enough at the right angle, the phone will go into orbit. And if I'm really feeling aggressive, I can throw the phone hard enough to reach the moon. That's classical mechanics. This is quantum mechanics, so things are going to be a little different. And because it's different, we have all new options in terms of gates that are available to us. All right, so with that quick explanation of qubits and how do they work, I am going to sign off. If you have any questions, please let me know in the comments or reach out to us. And once again, my name is Frank Lavinia, and you have been listening to Impact Quantum, podcast for engineers who are curious about quantum computing. Thanks, and have a great day. All right. Thanks, everyone, for watching this live on LinkedIn, YouTube, and Facebook, and all this platforms, Twitch as well. Really appreciate it, and definitely would like it if you could support the show by going over to liking our page. I think we have a page on Facebook now, and all sorts of other stuff. There are no questions in the chat window, and I have a meeting that starts in about 30 seconds. You have a great day.